All right, here we are. Short and sweet. After spending a bit of time, perhaps mired in computational detail, right? Getting our hands and our fingers and our thumbs and our limbs all dirty with binom PDFs and normal CDFs and lots of number crunching type calculations. We're going to take a step back, and we're going to try to get a glimpse of the forest rather than the trees, which we've been studying for a large part of Chapter 4 up till now. Let's try to get a sense of the big picture, and then let's start trying to connect some of what we've learned to this big picture. So, this is sort of hearkening back to that first chapter we talked about, right? What are some of the types of questions? What are some of the inquiries that we can use statistics to try to address? Well, right, in terms of a descriptive approach, we might be interested in trying to determine, right, the mean first-year income of all nursing graduates. In terms of politics, we might be interested in the percentage of U.S. voters who favor a certain presidential candidate. Right? If we were a politician, we might be interested in the percentage of our constituents that would favor a certain bill, for instance. Or if we're a fish enthusiast, which is what I think maybe it's called an ichthyologist. Hopefully I'm not wrong about that. We might be interested in the average distance that a pregnant salmon swims upstream before laying her eggs. Isn't that cool? It's an interesting fact that for whatever crazy, zany reason, pregnant salmon swim against the current rather than with it to go forth and lay their eggs and make cute little salmon babies. So, reiterating much of what we talked about in Chapter 1. We cannot find and record the income of all nursing graduates, right? That would be an impossible task. There's hundreds of thousands, perhaps even millions of nursing graduates, and of course more of them are being born every day. So, with this in mind, what do we have to do? What is our compromise in the face of this reality? Our compromise is that we take a sample of some nursing graduates. Let's say, for the sake of argument, that we take a sample of 200 nursing graduates. We figure out how much these 200 nursing graduates make, and we compute the mean of our sample, right? We use the mean of the sample as our best guess for the mean of the population, of all nursing graduates. Now, this introduces a whole slew of interesting questions. First and foremost is how good of a best guess is it? That is the question that we're getting ready to pursue. Similar idea. Up until the actual vote, we cannot know the voting preference of all voters. So what do we do instead? What we do instead is we take a sample of some voters. We use the proportion of our sample that favors a certain candidate as the best guess to the true but unknown proportion of all voters who favor the candidate, right? So if before, say, our last presidential election, we took a sample of, say, 1,000 voters, and it turned out that, say, 57% of those voters, of our sample of voters, said that they favor Barack Obama, we then make a jump, we make a leap, we make an inference, and we say that our best guess for the percent of America who favors Barack Obama is 57%. Now, again, the question becomes, how good of a best guess is it? And that's the type of question that we're getting ready to explore as we end Chapter 4 and we start to wind up Chapters 5 and 6. Now, central to this discussion are two important ideas called parameters and statistics. So let's start with a parameter. A parameter is any number that describes the population. This is usually the value of statistical interest, and it can never be truly known without sampling the entirety of the population. So examples of parameters would be the mean income of all nursing graduates, or the proportion of all voters who will vote for Barack Obama, right? They make it easy for us. They almost make it a little bit too easy, right? It's like Like what? Like shooting fish in a barrel, although I don't know why anyone would ever want to do that. Right? We have population and we have parameter. It's alliterative, agreed? They both start with the letter P. P goes with P. Population goes with parameter. Contrast that with a statistic. A statistic is a number that can be computed from the sample, right, without making use of any unknown parameters. Statistics change. They vary from sample to sample. Statistics are generally our best guess for an unknown population parameter. So, for example, the average income of a sample of nursing graduates, the percent of a sample that will vote for Obama, right? So, again, they make it easy for us. It's still alliterative. Statistics go with samples. Now, the one mistake that people make is saying that the sample size is a statistic. It is not. That's where that second bullet point about statistics varying from sample to sample is important. A statistic is something like an average height, and if we took the same size sample over and over and over again, the sample size is not changing, but the average height, right, the average height of our sample, if we're taking different samples over and over, is probably changing slightly from sample to sample. That's what makes it a statistic. So, for example, years of extensive, exhaustive research has somehow miraculously shown that the true mean distance that all salmon swim upstream is 45 meters. That is, the true mean distance that all pregnant salmon swim before dropping their eggs is 45 meters. Now, a more humble approach takes a sample of a mere 100 pregnant salmon and finds that the mean distance swam by their sample of pregnant salmon is 47 meters. What's the parameter? What's the statistic? Well, in this example, the parameter, right, is the population mean. And that's example, it's 45 meters. The statistic, right, is the sample mean, which is 47. Now remember, sample sizes are not statistics, so the answer is not 100. It's the sample mean, which would be 47. Now, here are the most commonly used statistics and parameters. The most common of them all is the sample mean. We talked about this in Chapter 2. The sample mean, X bar, is a statistic. It's based off a sample. It's used as our best guess for the population mean, mu. It's our best guess for the generally unknown mean of a population. The sample variance, S squared, is a statistic. It's based off a sample. It's generally used as our best guess for the often unknown population variance, sigma squared. The third one, which this might be our first time looking at it, but we're going to see it again in Chapter 5 and also again in Chapter 6. The sample proportion, so it's like P with like a little, I think they call that a caret, like a little triangle above it. We verbalize that as P hat, because it looks like P with like a little birthday hat or a party hat. So the sample proportion P hat is a statistic. It's the percent of a sample that has some characteristic of interest. Maybe the percent of a sample that's defective, maybe the percent of a sample that favors Barack Obama. It's used as our best guess for the generally unknown population proportion P. So P hat is a statistic. It's used as our best guess for P. Now, here's the big idea as we wind down this PowerPoint. It's something that I want you to think about. It's easily said, but perhaps not so easily understood. S squared, X bar, P hat. They're all statistics, which means that they are numbers generated from randomly selected samples. Remember, again, hearkening back to Chapter 1. In Chapter 1, we talked about what are the properties of a good sample. What makes a good sample? And we said we want a good sample to be representative of the population, and we want a good sample to be randomly selected. We said all good samples need an element of randomness to them. It's this randomness that gives these statistics the properties that we need them to have. It's this randomness that makes them statistics. Because they're generated from randomly selected samples, what does that mean? What does that imply? It implies that these statistics, say the sample mean for instance, the sample mean takes different values with different probabilities, right? Say I'm interested in the average height of all Westchester students. And we have some 8-foot tall student, Bob, who happens to go to Westchester University. Now, if I take a sample of students, there's a certain probability that Bob will be in my sample. There's a certain probability that Bob will not be in my sample, right? And depending on whether or not the gargantuan Bob is in the sample or not in the sample, I'm probably going to get a different sample mean or a different average height for my sample, right? So again, the statistic, the sample mean, takes different values with different probabilities. Now, this is the whole point of Chapter 4. If something, some random phenomenon, is taking different values with different probabilities, that means it's a random variable. Statistics are random variables. Since they're random variables, well, what do we know about random variables? Random variables have 3 characteristics. They have a probability distribution, they have a mean, and they have a standard deviation, right? So statistics have a probability distribution. This is given its own special name. It's called a sampling distribution, and that's what we're getting ready to talk about. We're getting ready to talk about the sampling distribution of statistics, particularly the sampling distribution of the sample mean x bar. But also keep in mind, right, we're also going to be talking about other things like, remember, all random variables have means and standard deviations. X bar is a statistic is a random variable. So the sample mean is a random variable. It's easy to say, but it's hard to really wrap your head around that idea. And since it's a random variable, like all random variables, it has its own mean, it has its own standard deviation, which is kind of crazy because we're saying that the sample mean has a mean. We could talk about the mean of the mean. And the sample mean has a standard deviation. All random variables have standard deviations. So we could talk about the standard deviation of the mean, which again is kind of a crazy thing to say. But all we're saying is just the standard deviation of some random variable. What's the random variable? Oh, it's the sample mean. Meditate upon this, and we will return to it whenever you get around to opening up the next PowerPoint.